caps of positive curvature, and you arrange for the curvature to make a smooth change from negative to positive at the boundary geodesic of the cap. And so these examples were constructed by Donae, independently by Barago. And the simplest picture, there's also the simplest picture is when you don't worry about having curvature be continuous. You just make this be the pair of pants and the three caps be hemispheres. That was the first picture in this direction. And there the analysis is pretty straightforward. Because with the hemispherical cap, when you come to the boundary, you just reappear on the opposite side at the same angle. And it reduces to really thinking about the geodesic flow on a surface of constant negative curvature. The analysis when you have the cap with the curvature changing from negative through 0 to positive, that's subtler. So I think that's more or less sort of what I know about the ergodicity of geodesic flows, sort of in general. So I probably should have said some of those things in the initial lecture. So when we write the notes up, we might move that to the introduction, either the introduction or the conclusion. We'll see. Okay, now I guess I have to get back to work proving things. So the first thing I want to do today is to think about Jacobi fields in negative curvature. Assume that the sectional curvatures are less than root water minus b squared, which is negative. And I want to think about gamma geodesic, y will be a Jacobi field of that gamma. And I want to assume that let's assume that at time 0 this inner product is greater than or equal to 0. And this is not a random thing to look at. So one reason to look at it is that if you look at the norm squared of the Jacobi field, this is twice that product. So this assumption says that at time 0 the length of the Jacobi field is non-decreasing. And what we're going to see is that that property persists, and in fact the length grows exponentially. So I want to do a calculation. I think the calculation says I look at the derivative of that, which means I'm really looking at the second derivative of the length squared. So I use the product rule, and I get y prime with y prime plus y with y double prime. then I use the Jacobi equation. So this will be minus the inner product of, and I think I also reverse the order in the inner product. Okay, what we have here is basically a sectional curvature, except that y probably isn't a unit vector. But if I rescale y to become a unit vector, then I do get a sectional curvature. But I've got minus a sectional curvature, which is going to be something positive. So we can see that what we have is greater than or equal to. If I've got two y's, so there will be the norm squared of y, and then times a sectional curvature. And the sectional curvature is less than or equal to minus b squared. So minus it is greater than or equal to b squared. So we get that. And now we can see from this that this derivative is actually positive. Well, unless these guys are both zero, in which case we're dealing with the Jacobi field that is forever zero and is not of any interest. So we can assume that this is positive. We can also say that this is like two terms of, I think it's the inner product of y prime minus by itself. Yes, I want to think about that inner product, which of course is greater than or equal to zero. And so thinking about that, this fact will tell me that I can read that this, what we've got here, is greater than or equal to twice, 2b times y with y prime. I think I've got that right. And so if you compare this with that, this is going to tell us that y prime. So if if y prime is greater than or equal to 0 at t equals 0, and y of t is not identically 0, then y prime of t is going to grow exponentially. For t greater than or equal to 0. You look as though you're sort of working through a calculation, something like that. So is there a question?
No question. I just
okay. So you can. So this is the sort of standard thing. But if I think what I get is that the the derivative divided by the thing is greater than or equal to something, and so you get that the derivative. If you work out what this is, we've got the derivative of log of y prime greater than or equal to b. So we get exponential growth, and we get a uniform. We get that the rate is at least 2b. So we know about something about how fast this quantity grows. Well, that isn't really the quantity that I want to think about. The quantity that I really want to think about is this. Because this is the square of dvt xi, if y is the Jacobi field determined by xi, this is the Sasaki, product. But it's obvious that y plus y prime with y prime is greater than or equal to twice y prime. So we do get, so this is going to grow, if this grows exponentially at a certain rate, so does that. So what we see is that so mu d phi t xi squared, which is y xi plus the end product of the derivative itself with itself grows exponentially. At rate greater than or equal to 2b if y prime at 0 is greater than or equal to 0. So, so there are another nice thing that is clear from these calculations is that even if I know nothing about the Jacobi field y, what I get here is positive unless I've got the identically 0 Jacobi field. Mm-hmm. So this calculation shows that the length squared of a Jacobi field is a convex function, which is a nice property. I think convexity of the length of all Jacobi fields, or the length squared of all Jacobi fields, I think characterizes curvature less than or equal to 0, at least non-strict convexity. So we get a nice idea about how Jacobi fields grow. If I have a Jacobi field and its length starts to grow, it is going to keep growing in length and it's going to grow exponentially. So that's good to know. So that means, so one consequence of that is that if I have a Jacobi field that is initially 0, obviously its length starts to grow. It's not the trivial one that stays 0, and then it's going to grow exponentially in length. And we have a uniform estimate that is based on the lower bound. I guess really an upper bound for the negative curvature. So it's a lower bound on the strength of the negative curvature. And maybe it's worth remarking that if we look at the norm of y of t, or yes, we're looking at the square root of these things, and this grows at rate greater than or equal to b. And so we discover that there are a lot of vectors xi for which you get a growth rate of at least b. So that if you think about, if I put xi equal to, so if I put xi equal to 0, comma b, oops, I want just parentheses. So any initially vanishing Jacobi field is going to have this growth rate. So we find a space, there's going to be a space of dimension, minus 1 dimensional space of Jacobi fields that grow exponentially with rate, at least b. So we get lots of exponential growth things. And because because volume is preserved, if something grows exponentially, there's going to have to be something else that's shrinking exponentially to compensate for that. And basically, you can get exponential growth, exponential contraction by taking something that's exponentially growing and following it backwards. And the geodesic flow is sort of reversible. If I take the geodesic and go backwards on it, that's also a geodesic. So we have, although I think it's easier to detect exponential growth, but that's going to force the presence of contraction as well. Okay, so I have some initial statements like that. Yeah, that one. Now I think I want to say something about horospheres. So I drew pictures of horospheres in hyperbolic geometry, where you've got an explicit construction. If I just know that I have sectional curvatures that's going to equal to minus b squared. And now I want to look at the universal cover. The universal cover by the, I guess it's the Cartan-Ardernal theorem, is it's diffeomorphic to Re. The exponential map is a diffeomorphism. But so if I have a geodesic gamma, suppose that's a geodesic in tilde, you can make a construction where you pick, let's say, gamma of 0. And now I look at gamma t, and I can draw the sphere. And I guess I should have mentioned that the universal, which I think you mentioned in your lectures, I'm sure, that in this situation there is, if I have 2 points in the universal cover, there's a unique geodesic segment joining them. So I can draw various pictures without having to worry about various things. So I can draw the sphere of radius t, centered at gamma of t. And then if I make t increase, these spheres increase. And the proof is about one line using the triangle inequality. Or maybe it's just a picture. I have gamma of 0, gamma of t, gamma of t plus a. And then suppose I have a point here where that distance is t, that distance is t. This distance here is a. I have a triangle. I have the triangle inequality. This is less than or equal to t plus a, which means that the sphere centered here with radius t plus a goes at least as far out as here, and in fact further really. The only time you get equality is when you're on this geodesic. So you get this picture of nested spheres. And so the horosphere is the limit as t tends to infinity. Actually, this is the stable horosphere. Is the limit as t tends to infinity of the sphere. Spheres with center gamma t and radius t. And then there's a parallel construction using the other half of the geodesic that produces an unstable horosphere. So I now want to claim that these horospheres are actually quite nice objects. So in the hyperbolic case, they're very nice objects. Now they're circles in the Euclidean, in the disk of the upper half plane model. What I want to show here is that these things are C2 surfaces. They're actually usually even better than that, but the geometric argument I want to do produces C2. So let me start by just thinking about what I was doing. I have there's gamma of 0, and I have gamma of t, and I get the sphere through there. And as t goes that way, this sphere kind of bends less and less. And all of these spheres are tangent to they're all perpendicular to the geodesic, so they all have a common tangent space here. But if you look at the second fundamental forms, or maybe I'll call this sphere S10. This changes monotonically. The sphere keeps bending towards the manifold formed by all the geodesics that go through gamma of 0 perpendicular gamma of 0. So these spheres, they all bend in the direction of gamma, but they do it less and less as t increases. And you can meaningfully talk about monotone convergence. If I look at, so if ut is, let's call this the second fundamental form, ut. So if I look at ut1 minus ut2, this is a difference of two symmetric matrices. And I can say that this is, I think I want to say that it's less than or equal to 0 if t1 is less than or equal to t2. I have to, so I think for this to be right, I have to arrange, well, this is correct if I interpret, if I interpret it so that u being positive definite means that the sphere bends this way, then I think I've got the statement that I want. And so you can see, and then we have sort of u, so we have u of t decreases as t tends to infinity, and we know that ut is greater than or equal to the 0 symmetric matrix. That corresponds to the hyperplane formed by the geodesics perpendicular to gamma.
Need some identification of the horospheres. The UTs are defined on different tangent spaces, right?
At the moment, I'm only using this one point.
Or 1 point.
Yeah, things are a bit trickier out here. I'm doing something easy first. So yeah. So I should have said add gamma of 0. Thank you. So I'm just thinking about this one point where they all go through that one point, and they sort of bend less and less, and they're constrained to be to the right of perpendicular to the geodesic. So you get this sort of nice monotone convergence. And you can actually see that this convergence is uniform. Because if I look at the difference between these two things, if I think about Jacobi, if I think about the picture of this is meant to be a picture of Jacobi fields. Of course, it looks like an infinitesimal picture of geodesics. So if I start off with initial value, well, initial value, if I have y, norm of y of 0 equals 1, and you might vanish at time t1, or you might vanish at time t2. If I look at the difference between those two Jacobi fields, it's a geodesic that's initially 0. Sorry, it's a Jacobi field that's initially 0, and by what we've seen is going to grow exponentially at least a certain rate. And we know by the time it got to here that it hasn't grown very much, because one of our Jacobi fields has become 0. The other one has not become any bigger than it was to begin with. So this gap has length less than or equal to 1. So sort of the difference of the two Jacobi fields grows exponentially, and after time t1 still has size at most 1. So that means that it means that the initial derivative of this difference Jacobi field had to be very small. And so that's the idea that you can use to show that this convergence is actually uniform. So that's the easy thing. And this argument works uniformly for all geodesics, because we've got this uniform estimate. So we get uniform convergence of and now you can think about, if I go back to the picture that I have here, let me draw the limiting guy, so pink. What you want to do now is to say, let's think about a geodesic, about a point here on the limiting sphere. What can we, if we think about that geodesic, what I would like to know is that what I'd really like to be able to do is to just copy what I did here for this geodesic. But what I really know is that I have vectors that are converging to this one, but they're not doing it necessarily along that geodesic. But I do have the uniform convergence of the second fundamental. So the second fundamental forms for spheres. As the radius of the sphere gets large, the second fundamental form gets closer and closer to the one for the horosphere. And if I look at a sequence of Jacobi fields, if I have Y(n) is a Jacobi field along gamma in here, and I know that Y(n) of t, let's say it decreases from 1 to 0 in time t(e), and I know that gamma n, the initial tangent vector of gamma e converges, say, to the initial tangent vector gamma, and I know that Tn converges to infinity. I'm going to get, and we might as well assume that yn of 0 converges to some initial. So you're going to get a limiting Jacobi field, and this limiting Jacobi field is going to be, it's going to start off with length 1, and its length is not going to decrease, sorry, isn't going to be non-increasing. And that will have to mean that this limiting Jacobi field actually decreases exponentially in length. So we can see that the limit of the second fundamental forms for our spheres, as these vectors converge to that one, the limit of them is going to have to be the second fundamental form for the surface here. So you can construct, sort of geometrically, construct these porous spheres, and then geodesics, the Jacobi fields obtained from the horosphere are going to be the ones that shrink exponentially, stable horosphere. So we have a geometric construction of stable horospheres. And then for the, if you do the same thing for the other direction of the geodesic, you get the unstable horosphere. Okay, so that's the sort of geometric way of thinking about stable and unstable things. Now I want to kind of switch to the dynamical way of doing things. So there's the idea of a Nozzle. So I want to have I might try using, I'll use E from X will be a compact manifold. F will be a diffeomorphism. So I'm going to give the definition for diffeomorphisms first, and then it'll be easy to see how to adjust the definitions to talk about it and also flow. And that's going to that will capture the essential behaviour of the geodesic flow and negative curvature, which is really why these definitions were made up in the first place. So if is a Nozzle, if there is I think the word continuous, I would say invariant, and I believe I don't need both words. I think I can leave out one of them. I can leave out whichever one I prefer, but I can't leave both of them out. So you have a splitting of the tangent bundle. So the tangent bundle to X looks like ES plus direct sum EU. And invariant means the derivative of S applied to something in ES gives you something in ES. And of course, same for EU. So you have such a splitting. And then the splitting has, the important stuff is what comes next. It's the properties of vectors in these bundles. So I can have between 0 and 1 will work, what I want to say. So there are constants, so right. Now we finally get to the punchline. The idea is that vectors in here shrink exponentially as you apply the diffeomorphism going forwards. And vectors in here shrink exponentially as you apply the diffeomorphism going backwards. So that the norm of the f to the n v is less than or equal to c times lambda to the n times the norm of v if v is in es, and norm of the minus e of v is less than or equal to c lambda to the n if v is in EU. And this is meant to be true for all n greater than or equal to 0. So this says that if I have a stable vector, it's going to, and I keep applying the derivative of f to it, it's going to shrink exponentially because lambda is less than 1. This definition and this, and the norm, the idea is that you have, you just pick a Riemannian metric. So, Riemannian metric. If I pick a different, if this works for one Riemannian metric, and then I pick a different Riemannian metric, the same thing will work. I may need a bigger C, and I think I might have to make lambda just a little bit closer to 1. But if I make lambda, as long as I make lambda just a little bit bigger than it used to be, and pick C big enough, it will still work for a different metric. And it's also possible to reformulate this definition by, if I do the right things, I can choose the metrics so that I can arrange for C to be equal to 1. And it's often, if you're actually doing calculations with things, it's often convenient to say, let's assume we've chosen the metric for which we have C equals 1. So with C equals 1, the idea is you immediately, even after one iterate, you see contraction. And in general, with a general metric, you can't hope for that. You can only expect to notice contraction after you've done enough iterates. And the way you construct the metric for which you see contraction immediately is you start with some metric, and then you define a new metric to be something like, I think you can just take something like the and I think you may want to put some weights on these things. But I think if I just use something like, you do something of that nature, and the idea is that when you apply df, this term disappears and you get a new one at the end. And what appeared at the end is a lot smaller than what you had at the beginning. And I think you usually put some, I think you're supposed to put some factor, like, I don't know, lambda to the, or lambda to the k in the kth term, or lambda to the minus k. I can't quite remember which, but you can do something like that. So there are, this is, I'm not quite sure if I've remembered that correctly. But you can, the idea is that you can basically think that these vectors shrink when you go forwards, those ones shrink when you go backwards. And in the geodesic flow, well, so that's the Nozzle diffeomorphism. And then for an Nozzle flow, you have the same thing, essentially. You have, except you now have Tx equals Es plus E0 plus EU. And E0, this is one-dimensional tangent to the orbits of the flow. And then these are transverse to the flow, and this kind of behaviour happens. Whereas if I have to express it with, I have something like in ES, I have norm dV less than or equal to C or although I probably shouldn't have used lambda. What's a suitable letter? It sounds like a number that's between 0 and 1. Let's have kappa. And what I want to have here is I want to have lambda positive, and then what I'll have here is e to the minus lambda 10 times normal thing. No, so probably what I should have done here was say lambda positive equal e to the minus lambda real. That might have been a better way to write it. And then the number that I called kappa a minute ago is just e to the minus lambda. And so for the in the geodesic flow, if you use the negative curvature, if you use the Sasaki metric, ES consists of Jacobi fields that come from the stable horosphere. So you have your stable horosphere. You vary the geodesics through geodesics normal to the horosphere, and you're going to get a Jacobi field that contracts exponentially in future time. And in fact, you get immediate contraction. The C can be taken to be 1 with the Sasaki metric, and then EU comes from the unstable horosphere. So these definitions abstract the driving property of the geodesic flow. And pretty much once you've gotten to this structure, that's the end of the role of the geometry in proving the ergodicity of the geodesic flow. And so I think what I'll do now is switch to thinking about a Nozzle diffeomorphisms, because I don't have to mess with the central bundle. Perhaps I could mention at this point that there are generalizations. So this notion of a Nozzle diffeomorphism, so the Nozzle property also goes under the name of uniform hyperbolicity. Hyperbolicity is what we're seeing here, that you've got some things that contract when you go forwards and other things that contract when you go backwards. The uniformity refers to the fact that the same lambda works for every orbit. Non-uniform hyperbolicity would mean that you have this kind of thing happening on a suitably large set of orbits, say a full measure set of them or something like that. But the lambda may depend on the orbit. And there could be a set of bad orbits for which there is no lambda. And that kind That's exactly the sort of behaviour you see in non-positive curvature. Well, which that you can see. So if you have something like a surface, suppose you have a closed geodesic round the middle, where the curvature is equal to 0, there is no hyperbolicity at all on that closed orbit. And orbits that spend a lot of time spiraling around near that closed orbit are going to have a lambda that's very close to 0. So that's the idea of non-uniform hyperbolicity. There is also the idea of partial hyperbolicity. In partial hyperbolicity, what you do, so full hyperbolicity, you've got a splitting of the tangent bundle. In partial hyperbolicity, the way I like to think of partial hyperbolicity, what you do is put in a third bundle. And the vectors of the third bundle do whatever they do. They may contract as you go forward in time, but they don't contract as strongly as the stable ones. And they might contract if you go backwards in time, but they don't do that as strongly as the unstable ones. So you have a central subbundle in which you see intermediate behaviour, which could be contraction, could be expansion, but it's weaker. And so one natural example of something that's partially hyperbolic is to look at your Nozzle flow and take the time 1 map. And for the time 1 map, this of course is the central direction, and there you get actually neither expansion nor contraction. But that's sort of rather nice central behaviour. And so quite a lot of the ideas that make hyperbolicity work, many of them extend to the situations of partial hyperbolicity or to non-uniform hyperbolicity. The ultimate subject should really be non-uniform partial hyperbolicity. I don't think there are too many results yet that you could really view as genuinely non-uniform partial. Right, so far, so you have sort of uniform, you have partial, you have non-uniform, and those results seem to fall either, that aren't for uniform seem to fall into one category or the other. But really, eventually, what has to be understood is non-uniform partial hyperbolicity. Because really, this is very special. These are still rather special. This is starting to get genuinely pretty general.
Last time you had spoken about the Weil-Petersen geodesic flow.
That fits into this non-uniform. So in the Weil-Petersen geodesic flow, that fits into here with some extra difficulties. So you have, in that case, you have sectional curvatures that are all negative, but the sectional curve except in the simplest cases where the Teichmüller space just has real dimension 2, you get sectional curvatures that range all the way between 0 and minus infinity. So the presence of the 0 sectional curvatures means that you do get orbits along which you have very weak hyperbolicity. And then there's the added difficulty that in the Weil-Petersen geodesic flow, it's not a complete manifold. And there are orbits that go to infinity, except that infinity isn't at infinite distance, it's at finite. The end of the world, if you go in the wrong direction, is only this far away. And there are geodesics that go there. And so there is a recipe for what you have to do. You have to understand how badly things decay. Well, you have to understand that things don't get too bad too quickly as you approach the end of the world. And then you can deal pretty much. So there's a standard sort of theory of non-uniform hypervelocity. It's known as Hessian theory. And so as long as, in the Van-Petersen example, as long as you can prove that the relevant things are really the curvature and the derivative of the curvature, if they don't blow up, if they don't go bad too quickly as you approach the edge, then this can be reduced to more or less standard Hessian theory. There is a book by Cutoff Instruction. It spends about 100 pages. They're very difficult to read.
What do they do?
They prove that even when you have sort of singularities, so the Van-Petersen metric, the simplest surface that you have is actually the modulus surface. So you have a cusp and you have two cones. The cones are a minor inconvenience. You lift to a finite cover and the cones disappear, but you're still left with the cusp. And the problem is the cusp has finite length. And so orbits, the geodesics that head straight to the cusp come to an untimely end. And as you approach the end of the cusp, the curvature goes to minus infinity. And in higher dimensional tubular spaces, things get not too much worse. But so what you have to do is provide estimates on how fast things get out of control as you go here. What you need is, if you have some quantity and you have a suitable measure of the size of the quantity, you want to know that this is less than or equal to some constant times distance from x to the boundary to a negative power. So if you have sort of, this is kind of sub x, well, it's better than sub exponential. It's like 1 over a power type of blow up as you approach the edge. And as long as you have estimates like that, then it turns out to be as good as the kind of uniform estimates.
So you're saying that you use those Kaplan's first theory that to kind of for the right weights and
Yes. And so this has existed since about 1985. So as far as dynamics is concerned, in some sense, Van-Petersen was done. All the geometers had to do was figure out the geometry. But that was hard. And so really the hard work was done by Scott Walbert. He has written a lot of papers in which he's made a lot of calculations about the Van-Petersen metric, about how the curvature of it behaves as you approach the boundary, about Christoffel symbols. So when we started thinking about it, we had all this information from Scott Walpert. Really the only thing that he didn't have was the derivative of the curvature. And we were able to find a cheap argument that got this kind of control on it, actually in the derivative of the curvature. But it turned out that for the curvature itself, we needed the estimate that Walpert was given, because they didn't just give an estimate of this type. It gave the correct P, and that was essential. So that's a sort of sketch of where that fits into things. And the results that I mentioned about non-positive curvature, they were one of the initial applications of SM theory. So I'm not aware of, I don't think there's too much application. Well, there is an example of a geodesic flow that is genuinely partially hyperbolic. So the time one map of, if you, I might as well, I think I'm going to put off doing any really hard work now until after lunch.
Okay.
So if you think about the time one map of an Nozzle flow, you get something that is a partial hyperbolic map.
Because you'll have to work with either ES and direct sum of these.
So if you want to prove that the time one map of the geodesic flow is ergodic, there's a sort of
So are you saying that you will have to then work with either stable and the weak unstable, or weak stable and the unstable?
Well, so if we think about the time one map, you've got a picture of, you've got the center for reaction. You have stable and unstable. These are what are called the strong, stable and unstable flow. And in the flow case, you can just say, well, if I've got something that's constant on, if I've got an invariant function that's constant on WU, it just flows along, stays the same. If I apply the time one map, it's the same if I jump by time one. But what if I jump by time a half? And so you have to, what you need to do is investigate what happens. So you get sort of things behave nicely if you go along stable or along unstable. And then you start looking at paths where you do some stable, some unstable, some stable. And you need to, you can show that it's fairly easy to show that by moving along stable and unstable, you can move anywhere you want in the unit tangent bundle. And this property, so there's a notion of accessibility. So any two points, in this case in T1 EM, are joined by a path consisting of finitely many legs, each of which is tangent to a stable or an unstable leg. That's the crucial property that you have to verify. And then there was a sequence of theorems. initially by Pynchon, and the most general one is the theorem that Amy Wilkinson and I proved. And they sort of say that if F is partially hyperbolic, has accessibility, preserves a volume of is C2, and then F is ergodic. That's the nature of these theorems, and I won't talk about what ... is, except to say that in the initial theorems there were very strong restrictions. There is now really just one restriction, which is not too restrictive, but it's still a restriction. And there doesn't seem to be, well, the restriction is very, very important for the proof of the theorem. It shows up twice in the proof in somewhat independent places. But there's no reason really to think that the theorem needs extension. It's just the current proof. So yeah, that's the nature of those theorems. So they discuss things like the time one map of the geodesic flow. And the other thing that you can prove using this type of theorem is that if you take the time one map of the geodesic flow for negative curvature, if you look at the hypotheses of the theorem, they're all satisfied for that time one map. And then if you perturb the time one map a little bit, well, you have to perturb it so that it still preserves volume, and you have to keep it C2. But otherwise, all the other hypotheses in the theorem are stable under small perturbations. So you get that not only is your time one map itself ergodic, any other diffeomorphism that's close enough to it is also hyperbolic. Actually, that's something I should say also about the Nozzle condition. If you have this setup, and I take the diffeomorphism F, and I make a small perturbation with C1 topology, then this is all going to work still. The bundles will change a little bit, but so this is a robust condition. And the property of being in an oscillator flow is also robust. Right, so I think that might be a good place to finish, and I'll have to start doing, well, I'll continue after lunch. So let's finish there for now.